It's not like in June. Right.
I know it's been warm. There we go. All right. So we're going to talk some more about alpha carbons today. So first off, start with a little bit of review. For enolates, for the most part, remember that enolates are a more useful form than just the enol. We can make an enol from any class 2 carbonyl, but they're not necessarily all that effective unless we make the enolate, because the enol is still just going to give us a resonance structure that's partially reactive, but it's not as useful synthetic. The enolates, because we get this full negative charge, even if it is in a resonance structure, it's going to be a lot more effective in terms of predicting what our reactions are going to be. So, and just as a reminder, if we just have a standard ketone or aldehyde, if we use a normal base, strong base, not super strong base, we're often going to get both the enolate and the ketone at equilibrium, which has the possibility of reacting with itself. In that reaction, we're going to spend a lot of time with today. It's called the aldol condensation, because it makes a molecule that has both a carbonyl and an alcohol, so aldol. If we want it to be an irreversible enolate formation, so really 100% yield, really useful synthetically, we're going to need to use sodium hydride or LDA, which are lithium diisobutylolide. Both of them have much stronger pKa's, and the sodium hydride makes a hydrogen gas as a byproduct, so it drives the reaction to completion. If it's a beta diketone or dicarbonyl, then we don't necessarily need the LDA. We can just use NaOH or NaOET or methoxide or any of those as a way to deprotonate that alpha carbon that's in between both of the carbonyls. So the reaction we didn't get to yesterday, before we do some practice, is if we can make an enolate, that also means that this alpha carbon winds up being a pretty reactive point, because what is the enolate going to look like for this molecule, or cyclohexanone? Maybe even, I suppose, for this case, we can just make the enol since we're under acidic conditions. What is the enol going to look like?
I can answer this question.
And then try to draw the mechanism under acidic conditions.
The oxygen is going to go single bond.
Correct?
And the double bond is going to
Bingo. Right, so draw that mechanism for that, for practice.
under acidic.
Under acidic conditions.
And these are all durable waste.
Correct. So first step, proton transfer to protonate the oxygen. Second step is another proton transfer as an elimination. And then you move so we pull the hydrogen off of the alpha carbon, move the electrons over towards carbonyl carbon, and the oxygen pulls the electrons towards itself.
I did that, but in 2 steps, like I did resonance and then.
Yeah, that works. You can't do the resonance until after you pull this up. But if you did,
I pulled that up first and then I put the positive on the right.
So- you wouldn't want to pull the electrons up positive charge, because that leaves a carbon with incomplete valence that we don't need. Because if we do these two steps first, we at least wind up like that. But we don't really want a negative charge under acidic conditions, so it really makes more sense in this case to do under acidic conditions especially, to do that second step all at once. And then if you wanted to show the rest of the structure for the sake of the next reaction, good. What would the resonant structure look like?
But just a bit of oxygen. Oh. Yeah.
So it could have that resonant structure. But it's gonna we're gonna need all of these arrows to happen simultaneously. What's the next step gonna look like? We're trying to figure out, how the bromination happens.
But if we want them negative right now and be positive separately. That's it.
Could be, except that as it is, that would be if we had the bromine acting as a nucleophile. But bromine gas doesn't act as a nucleophile. Bromide acts as a nucleophile. It's got a negative charge. Bromine is typically an electrophile. So the negative charge will come in here and attack one of the bromines, so that the other one can leave and turn into a bromide.
This arrow go both ways or one.
One way. Because we're not going to preform any bromine-bromine single bond. So the fact that we broke a bromine-bromine single bond makes it not an equilibrium reaction. And then we just have one more. Proton transfer to get us back to the carbonyl form.
with the other one that it is.
That would be, proton transfers are pretty much all equilibrium arrows. Because we had a whole chapter on equilibrium of acids and bases in Gen Chem, right? Most proton transfer steps are equilibrium steps. The only time when we're not going to draw proton transfer step as an equilibrium step is if we have such a huge difference in pKa that we can treat it like it's irreversible, when even then it's not really irreversible. Right? There's really no such thing as irreversible reaction, just reactions that are so downhill in energy that it's impractical to try and force it the other way.
Must be related to the rinse.
You have a sore throat?
No, I have like. Mucus tastes like a better other like every clothes spraying in it.
Hot and salt water.
Oh, that's true too.
Like all the way as hot as you can stand it without burning your mouth, and as much water as salt as you can saturate into it. And then gargle that. And it actually changes the solubility of the mucus. So that it actually will dissolve and get out of your throat.
Mom was about to salt water fountain.
All right, so this is also one of the first cases of what's called an autocatalytic reaction. We needed acidic conditions for this to start, right? So the acid really is a catalyst here. It's acting just to get things going. But then over the process of the reaction, we're actually making more acid because we're deprotonating our carbon and turning it into more free H pluses floating around. So that characteristic, when the reaction produces its own catalyst, is what's called autocatalytic. Makes sense. Auto means self-sufficient or on its own. It's of great interest in terms of engineering and practical side of things, but autocatalytic reactions can really be dangerous because what will happen is you make more acid, so the reaction goes faster, and the reaction goes faster, so you make more acid. So you can wind up with what's called a runaway reaction pretty easily if you're not careful, and it's also exothermic.
So like those packets that are like instant cold, like smash them together. And would that be like this sort of thing? Is it like keeps going on its own?
No, because it doesn't keep going on its own.
Oh.
They don't last very long, right?
That's true.
All that is ammonium chloride, I think, as a solid, turning into aqueous ammonium chloride,
Okay.
which is an endothermic reaction. So as soon as it doesn't happen instantly, it doesn't run out of cold because it takes a minute for this to actually dissolve. But as soon as it's all the way dissolved, it's not getting colder.
Okay.
All right, so here's our cleaned up reaction. This one turn on today. We won't dwell on that. But just like we saw, this one actually does have it drawn as the resin step after the first step. I don't prefer this because as we discussed, but okay, the text goes through it that way, so I wouldn't mark it down for that.
So really, I'm on the textbooks level.
Yes, exactly. And then once we make that our double bond text bromine, we are not going to farm that. Remember that when we just had a straight alkene, we made that bromonium ion as our intermediate. So it was a similar approach, similar step to breaking the pi bonds. But we made an intermediate that looked like, that looks like this. It's gross. We don't need to do that in this case. Why? The oxygen lone pair can move down. So the reason that we formed this bromonium ion was so that nothing had a complete valence.
Oh.
Right, and we can, instead of doing that this time, we can just share the electrons from the oxygen instead. All right, here's a puzzle for you. If the carbons are asymmetric, the bromination will preferentially occur at the more substituted carbon.
For just a reason.
Why might that be the case?
Seems like opposite.
Based on, if we just look at sterics, you're right. But so remember our what are our two options for the enols here? It does have to do with the charges and resonance.
Okay.
Or we could also draw them as the resonance structures. They would look like those look significantly different.
I mean, the one on the left is more stable. Right?
Why?
Because it's more substituted.
So you're talking about this one?
Yeah.
Yes.
But is that what makes sense?
So that's a plausible reason. You answered the question. Yeah, it makes more sense. We're going to form this enol preferentially. It's the thermodynamically favored product. And since making the enol is our limiting, is our is reversible, it's going to form the thermodynamic product more often than the kinetic product. And once it gets here, our only irreversible step was the enol reacts with the bromine. And since we're more likely to have this enol, we're more likely to make this product. So the Tate says rule as applied to a more complicated system. Practice. These other react, what does purity do? What is the reaction? Seen it a few times.
Saw it on the.
Yeah. It's just it's a base, it's a weak base, not gonna act as a nucleophile. If I'm remembering correctly, I believe that this one's pyridine. So it's a base, but it's too big to be a nucleophile. So it's not gonna give us any side products, any addition products. It's just there to counteract the extra H3O plus at the end. Because this is autocatalytic reaction, right? So we're gonna make a whole bunch of acid. We want to neutralize that at the end. It's also the purpose of the H2O. The phosphorus tribromide is going to basically do the same thing. It just makes the bromine more reactive. No, sorry, getting back. This one's a review. That's carboxylic acid. What does carboxylic acid do with bromine?
It replaces the one wash.
Close. I replaced that. Basically, this is announced. Remember how we said SOCl2 was a good way to turn a carboxylic acid into an acid chloride. Same thing. Except we're going to make an acid bromide.
Are we doing just?
Yeah. This one is on here because I realized we didn't spend any time talking about that. That is another one of those acid derivative reactions. It's on the reaction summary, but we didn't specifically talk about acid bromide versus acid chloride. They react pretty much identically. We just have to make them a little bit differently. Instead of SOCl2, we use bromine PR3.
PPR3. The P in the middle.
So remember back when we
We had like a lot of this.
right. All right. let's look at some more complicated cases. So that reaction where we wind up with both our enolate and our ketone present at the same time. We did a practice with that where we said, well, what happens if they react with each other, right? We're going to get something like, okay, well, this is now a strong nucleophile, so it can come in here. We're going to get something that looks like two of these added together, except it's not exactly going to be two of these added together, because one of those carbonyls is going to turn into an alcohol. So we're using the enolate as a nucleophile to do an acyl substitution. Sorry, an acyl addition, which is back from our aldehydes and ketones chapter. So we're going to wind up with something that looks like this one in our maroon color. I'll draw the other one in teal. Our product of two acetones reacting together, it's going to look like the alpha carbon from one acetone from our enolate goes and adds to the carbonyl carbon from our ketone or aldehyde. So we get something that looks like this, which then, if we follow it up with a proton source, we get this product. By far, the trickiest thing about this is keeping track of what alpha carbon is going to add to the carbonyl carbon. So our alpha carbon from the enolate, our enolate is going to stay as the carbonyl. And the carbonyl carbon that gets added to gets turned into an alcohol.
What's this called?
This is called an aldol condensation. So this product is called an aldol, even though this isn't an aldehyde. Basically, if it's a class 2 carbonyl, aldehyde, or ketone, we call this an aldol. And condensation just means that we took two things and we stuck them together into one larger thing. So condensation, because like if you picture two water molecules running into each other and sticking to form a water droplet. So this aldol condensation happens anytime we take a class 2 carbonyl that has an alpha carbon with hydrogens and we expose it to a base, especially if it's not one of these super strong bases. We use one of these super strong bases and we only get the enolate, this doesn't happen. Right? We need both of these present at the same time for the aldol condensation to happen.
So you need to not and the
Not an enol, just a ketone or an aldehyde. Right. If we try to do this with two different class 2 carbonyls at the same time, We use aldehydes for these more than others just because they're more reactive to the ketones, the reaction time factor, but again, it's could be with ketones as well. Oh, there we go. I figured out how to turn it on. Should turn on in a sec. There we go. Alright, so if we wanted to do these, to have two different class 2 carbonyls react together, we wanted to do a cross aldol condensation. We call it cross aldol condensation, trying to get these two molecules to react with each other. The problem with that is, unless we're really careful about how we do it, we're going to wind up with at least 4 different products. Because we'll get the red condensing with the red, the blue condensing with blue, the blue enolate reacting with the red carbonyl, or the red enolate reacting with the blue carbonyl. All similar products, but all distinct products from each other. Which, if we didn't mind separating these out and getting at most 25% yield, then I guess we could consider this useful. We don't usually like that though, right?
Right.
So how could we get around this issue? I'll go back to that other slide. We needed both of these presents for the aldol condensation to happen, right? So if we want to make sure that we don't get this and we don't get this,
But then we react with each other anyways.
why do you say that? What if instead of putting all 3 of these in the pot at the same time, we did something like make enolate first, irreversibly, using one of our strong, super strong bases, and then expose it to the blue one. So instead of, if we don't have all of these present at the same time, we don't have a mixture of this enolate and this carbonyl, this enolate and this carbonyl. We only have the red enolate, and then we follow it up adding the blue carbonyl. Or if we wanted to make this product, we could do the blue carbonyl and turn it into an enolate before adding the red carbonyl. So using those irreversible enolate formation is going to be how we do a directed aldol condensation. Or selective, I should say selective cross aldol condensation. We're getting very, very specific with our language here. So one way you can do it is to use there's basically 2 aldehydes that don't have any alpha carbons, these are that are commonly used. If we use benzaldehyde, it has an alpha carbon, but there's no hydrogens on it, so it can't form an enolate. If we use formaldehyde, we can't form an enolate. So in those cases, we can do this in a really directed way. And can only get one product. Well, not really though. Because we still have to deal with that because the blue molecule can make the enolate react with itself. So it cuts us down to only two products. As opposed to 4.
Yeah.
So still less than ideal, but better. Or we use LDA to make a permanent enolate irreversibly before we add this. Again, the key here is keeping track of where that black bond is. The alpha carbon of the remaining carbonyl is attached to what was a carbonyl carbon. All right, so how do we make this molecule?
The bond that is in between the OH and the methyl group, they're not.
This one?
Yeah.
Right. So these are two molecules. Are so those are our two pieces. What order do we have to do things in to get them to react this way? Okay. Which one? Blue or the red? Well, the enolate is going to be the one that's going to attack the other carbonyl, right? So the fact that these aren't symmetric tells us the order does that, right? Because we had an OH on one side and a carbonyl on the other. So which one is going to remain a carbonyl? The enolate that acts as the nucleophile, or the carbonyl that is the target of the nucleophile? One that's the target of the enolate is going to be this. Let's work back. There's two options, right?
Yeah.
If we take the blue molecule and we turn it into an enolate, we get this, which is then going to react with this. So we have this over here. Move up. Is that the way we want it?
Yeah, because we want the red one to be common for wage and get rid of the double one.
Exactly. If we did it this way, we're gonna make this enolate, which then attacks.
The top ones. So,
Top one is what we want.
because then that would make it blue one have the wage.
We don't want the blue one to be the OH at the end. We want the red one to be the OH at the end. So we don't want that one. Then our final product, or our next intermediate, I should say, is gonna look like this.
That's a managed for contracts overall.
It was pretty fun. But he gave them to us, because she had like a room out, so she couldn't like chew. And then she was like, now she's fine, so she's like, I don't want these, they taste like shit, taste. And so Taylor was like, I want, and then Mikey drank like last night. I was on say he drank one of the strawberries.
All right, so our actual reaction, we were writing it out.
Wait, is that not actually the action?
No, it is. We're gonna write it up in condensed form. It would be this one plus LVA. 2 would be our red molecule. 3, just water as the proton source. So really, it's the trickiest thing about this is keeping track of which one goes first. But it's a pretty, all we really did is we took this mess of reactions that were all happening simultaneously. And we said, oh, but if we control what order they happen in and make sure that the first one happens to completion, everything else falls into place.
Makes more sense, I think, in practice.
Yes. Where it gets slightly more complicated is that these aldols are not very stable on their own. It's not, I guess, it's not that they're unstable on their own. They can be rearranged to be more stable. If you do this at high temperature, the aldol will go through a dehydration reaction to make what we call an alpha beta unsaturated carbonate.
But in alpha beta, it's different purpose.
What does unsaturated mean?
It has a double bond. So it's in between.
Exactly. So what would the alpha beta product look like here? Alpha beta unsaturated product look like?
we would count from the double bonded oxygen.
We count from double bonded oxygen, so there's alpha. There's beta. And it's a dehydration reaction. Which is a fancy way of saying elimination reaction to evaporate water, right? So we're gonna kick off this OH, we're gonna kick off a hydrogen from the alpha carbon. To get the color coding doesn't mean anything now, I'm just using the blue pen because it's a good pen. Why would this be a stable compound? What makes this more, normally when we heat up alcohols, there's some amount of elimination that can happen, but usually we had to work at it a lot harder, right?
And typically we would say that a double bond is less stable than.
Exactly. So what is it about this double bond that makes it more stable? It's not electronegativity, it's
That's the only one I know.
resonance.
Oh, yes, oh, okay, yeah, that makes sense.
Right, because that can give us a resonance structure with two conjugated pi bonds now. So that anytime the most likely culprit for making a pi bond more stable than you would expect is almost always resonance. Okay, so it's a reaction we've seen before. We're not going to spend a ton of time on this mechanism. But if we do these reactions at high temperature, this is a far more likely product for us to see than this one. And I drew it as being reversible because it is, but this being so stable because the resonance means that this is actually favored.
Okay, so would our reactions typically go all the way to this? Okay.
Often. Yeah, most often. The way that I would write it on the test, if I wanted to see both steps, is I would do this in two steps. I would say, okay, with our arrows we had before, it was LDA.
And then like another.
And then another arrow that just showing heat.
Okay. So does it need cold to go back the other way or will it swap?
It needs cold and water. Because remember, high temperatures favor the more randomness, right? It's a doing an elimination reaction. It's favored at high temperatures because we make an extra piece floating around. More disorder
Yeah.
because we make a water molecule. So let's do one of these, and then we'll take our break and do the other two when we come back. Let's do A. So first, undo the alpha beta unsaturation, put the OH on there.
Is there gonna be your wrong, specific to if it goes like market.
Yes. Because we're specifically looking at what molecules reacted through an aldol condensation. So we need the OH group on the beta carbon.
Okay.
Okay, so our aldol look like this. Then what is the bonds that we form between the enolates and the carbonyl?
The one that done with the bond was.
There you go.
So we actually did.
Ready for this? And so we want to rearrange this so that it looks cleaner. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Which we would name as 2,6 heptane dione. So if you put 2,6 heptane dione under basic conditions with heat, it'll react with itself to make this mess.
So the first step would just, like, making the ring would just be HCl.
These are going to work better under basic conditions because remember we need to make an enolate, make it more reactive.
So,
OH minus. You can make an enol under acidic conditions, but they're going to be more reactive under basic conditions because you have more of that enolate present. So we really don't need multiple steps, we just need base. Or you can even do LDA. It doesn't particularly matter if it's LDA or hydroxylate in this case because it's already reactive. So the order doesn't matter as much. This one, on the other hand, looks like it will. This one, our double bond is on another ring section, so it looks like it's a case of it reacting with itself. But we'll find out when we come back from break.
ooh, cliffhanger.
All right, let's come back at 5 after.
Is this a step 2?
No, not a separate step. I shouldn't have put a number there. Normally with these aldol condensations, want to be paying attention to the order in the steps, but in this case, because it's reacting with itself, it doesn't.
I'm so jealous of mom right now. I want to be in, I love Maryland. I want to be in Maryland so bad. I want so bad. And so, still in the fall, and there's some like big little thing like right in the class and I realized they still couldn't fall around. There's a jealous, I said jealous. Oh, is that the one, is that the one that mom was like, was like, her later, and they were not. But let me just say one more thing before you go here, a lot of this morning that they're gonna have a lot. Oh, well, because it's also, like, I was trying to figure out where this wasn't gravel. It drove me crazy. So, now I know that it happens again. Okay, don't have to have it until we do all started. But we saw the PJ said that thing, and that's like, what's going on? I don't, not the same thing. But it's fine. I think we should probably like be there. Well, it should be, because I've already made all the words. That's too complicated. It's not awesome to me. And it was said a table will be provided. I like to be going back. I just gotta go like first shopping, go home, change, and then like you'll set. Yeah. Because it ends at like 2, so. I have to help you with the thing. The. And to ask. I'm getting a second husbands. I don't know to do that. To expect all of those things you really get.
He's called 100,000 Kingdoms, another N.K. Jemisin one. It might be more, it's got a little bit more of the romance aspect to it.
Wait,
I think it's called 100,000 Kingdoms.
I mean. Hey, yeah, but can you put him into the glass? Don't think they have that. But they have the other suits.
Yeah, the other one.
Yeah. Okay, back to here's my house.
Right.
Everything.
Try typing out the word 100,000 Kingdoms or Inheritance Trilogy.
It got slower than what was in it.
All right. That clock is way off.
Yeah, I know. I noticed that. It's been slowly.
It's getting worse and worse. I'm not gonna do that. I'll get this tool later. All right. How do we do the second one? So these are actually almost easier to find the black bonds, the bond because it has to be between the alpha and the beta carbons.
And why it has to be a double bond? That's the dehydration.
So yeah, when these aldols finish their condensation, if there's any heat, they're going to kick off that OH group and form a alkene instead. So we wind up with our aldol would look like this. And the molecule started it all. Would be hexane diol. Do we need to specify any numbers for hexane diol?
I feel like we should.
Is there any other way you could have two aldehydes?
Oh, because they have to be on the ends.
They have to be on the ends. So diol will never have numbers associated with the diol because you're defining the start and the end of your chain by where the aldehyde. Even if there's other stuff going on over here, we had something else going on over here. As long as we're going to use this as our parent molecule. Hexane diol has these numbers, we just need to specify what the propyl group is. All right, let's do the more complicated one. I'll give you a minute or two. Head start. And actually, while you do that, I just realized I double booked myself on Friday, so I gotta go talk to my boss real quick. Thank you.
Yes. So I choose later. But this should be. Why? Because that's how it starts, and then there's a little one to my head. But how do we know?
So the aldol would look like this. There's our alpha beta bond. So that's the one that's cut when we're working this backwards. So our two carbonyls are benzaldehyde and acetone. Now, what order do we do everything in?
We want the acetone to stay how it is, so it would make the benzaldehyde. Less.
I knew what you meant, but can we turn benzaldehyde into an enolate? Does it have any alpha carbons that have hydrogens? So the one that stays as the carbonyl is the one that gets treated with the LPA. So acetone, LBA gives our enolate plus benzaldehyde. Then this would come in here, push that away. And then follow it up with water just to propionate it. That gets us all the way to our aldol product. Which we then heat it. Is going to give us our alpha beta unsaturated ketone. So this is actually a pretty good way to put puzzle pieces together if we're trying to do a synthesis reaction, because there's a lot of different ketones and aldehydes out there that we can do this with. And it allows us to take larger molecules and put them together in a way that might be easier than using a Grignard reagent. And because once we get here, if we stop here, there's still a lot we can do with this, because we have ways to get the aldehyde or the ketone to react that leaves the hydroxide alone, or we can get the alcohol to react that leaves the ketone alone. It's a strong base. Pull up the structure. I would have said diisobutyl rather than isopropyl. Diisopropyl amide. So it's basically this molecule here. The L is for lithium. The lithium doesn't really participate. It's just a sterically hindered, very strong base. We want it to be sterically hindered so that we don't get it acting as a nucleophile. But any sterically hindered base in theory works with this. So in theory, you could use TBOK, except for the fact that TBOK is not a strong enough base to make the enolate irreversibly. Right, because all of our deprotonated alcohols, they're good bases, but they're not good enough to pull off these alpha carbon protons, unless it's one of those beta diketones. All right, so questions on these Kraft aldol reactions?
No, I like these ones.
They have a very set procedure that works pretty reliably. They're a bit of a logic puzzle, but that's kind of the fun. All right, let's talk about another type of condensation reaction. So far, we've just been talking about alpha carbons and aldehydes and ketones, right? But they're not the only carbonyl molecule or carbonyl functional groups that have alpha carbons. In particular, esters will also go through a condensation reaction. The interesting thing about the esters going through the condensation reaction is that they both stay as carbonyls. It's still a reduction reaction because we go from a carbon with an oxidation state of, I think that's +3 to +2. No, to 0. No, it is +2. So, but it doesn't look as obvious as the other one, where we very clearly had an alcohol and a carbonyl at the end. But they work the same way. Expose it to a strong base, to make an enolate, what would the enolate look like for this ester?
It wouldn't, the bond wouldn't go towards the other house.
Right, this is not an alpha carbon, right?
Right.
It's a position where an alpha carbon would be, but it's not a carbon, and it doesn't have any hydrogens. So there's our alpha carbon that we're gonna have react. So there's our enolate. Which, when it reacts with another molecule, we get a similar mechanism. So we get an
Did we start with Adelaide?
no, it's all reversed. What's the next step would be?
Wanted to stay in the double bond and all.
And we have a good leaving group attached to it, don't we?
The, wait. The OBT.
Not on our final product, is it?
Yeah.
Which also matches with what we know about carboxylic acid derivatives, right? They make these tetrahedral, the way we transferred between all the different carboxylic acid derivatives was you make a tetrahedral intermediate and then reform the carbonyl and take off the leaving group. Right, so that comes down, this leaves, and we get
Reversible.
reversible filling. This whole reaction is reversible. If we were showing the full mechanism, we should show that the enolate formation, which just looks like that. That gives us our enolate, which attacks another molecule itself. Forms a tetrahedral intermediate to our final product. And it's reversible because we made a strong base, the same strong base we started with, but that can also act as a nucleophile. If it acts as a nucleophile, it's going to come in and attack right there. And we're going to have each of these happen backwards. Right, so it's very easy to control based on changing the conditions. When we want this reaction to happen, if we want to make this product, we want it to happen at low temperatures or high temperatures. We don't want to make a water molecule. And this already is downhill in terms of entropy. Right? Because we started with two of these molecules separate. And then we forced them to come together to make one larger molecule. Two molecules making one larger molecule is always going to be unfavorable to entropy. So low temperatures is gonna favor this. If we took this and we subject it to high temperatures, it's gonna reverse. We might make some of that alpha beta unsaturated compounds. But that's gonna be a lot less likely because this is a ketone, not an alcohol. So it's not a good leaving group as this. So when we add the heat, it goes back that way instead. You can see the yield isn't even that great. In 75% yield is better than some of the reactions we do in lab, but it's still not great. So this is called the Claisen condensation. Claisen was very influential organic chemist in the early days. I believe we also have at least 2 pieces of glassware that are named after him. In fact, one of the ones that we use all the time. That little guy. That's a Claisen adapter. All right, so here's just our cleaned up mechanism. It's exactly what we just drew though. Make your enolate attacks into the molecule itself, tetrahedral intermediate, leaving group leaves. Then we do have an alpha carbon that is stabilized. So it actually is pretty easy to turn that into an enolate as well. So if we let the reaction continue, we're actually getting this. But that's why we always finish with adding some acid, because that takes that doubly stabilized enolate and turns it back into our condensation product. So what would we react to make these? What base would we use? Doesn't the base matter? Why? They're not symmetrical. This one we use epoxide as our base. What if we use methoxide as our base here? We have MEO. That connects to the base, but it can also act as a nucleophile, right? So we also would wind up with a side reaction where we convert this ester into a different ester. So we always want to use the same base as on what's on the other side of our, or same base as our leaving group that we're replacing. Whatever is attached to your ester has to be what we use as the base to avoid getting mess products. So basically, just look at that.
And that's our base, whatever is attached to our, or is whatever our unit is.
Yeah. So we want to use something that's TP oxide, which we more frequently call TPOK or potassium tertiary oxide. You're just saying it out loud. Not really particularly tricky. thing, but it's easy thing to miss. The base you choose matters for getting as much yield as possible. All right, what is the product of each of these Claisen condensations? Again, I'll give you a head start.
But this really. Right, and then, oh, this. It's not working. Matters. Oh, because we look from the.
I'm gonna reorient it. Be myself forward. So yes, we're gonna get the enolates. It's gonna look like that.
Okay.
Then when it reacts with another molecule. It's gonna attack the carbonyl. And I'm gonna draw two mechanism steps once to then take that off, right? So we're gonna wind up with.
And we just have two of them always, like.
But for now. That's to the alpha carbon. So the carbonyl carbon from one of the molecules attaches to the alpha carbon of the other. And the trick is really keeping track of what's attached to the alpha carbon. The alpha carbon is our active carbon in this case, right? So what's attached to the active carbon is benzene ring and then an ester.
Is it the active carbon below that would be like the attached?
Well, so I'm using active in the sense of the one that's doing the reacting.
Okay.
On the red molecule, the carbonyl carbon is not active, because it's not the part that's reacting. On the blue molecule, the active carbon is carbonyl carbon. Like that's how we use the word active, it's just to mean the one that's doing the reacting, or making new bonds. And so alpha carbon has a benzene ring attached, has our ester attached, made a new bond to the carbonyl carbon of the blue molecule. The active carbon on the blue molecule now no longer has this attached. It just has its alpha carbon in a benzene ring. Alpha carbon benzene ring. So. These condensation reactions, the Claisen condensation reactions, are similar to our aldol condensation reactions in that they can react with themselves to do this. But what was the next thing we added with our aldol condensation?
Dehydration.
Even before that, we added, what if we don't want it to be symmetric aldol condensation, right?
Yeah.
How do we control it if we want our red and our blue molecules to be two different molecules? And how do we do that with aldols? On the one that stays, that has the same functional group as you get. So in this case, you gotta be careful with the one that stays a carbonyl, because they both say carbonyls. But the one that stays as an ester is the one that gets treated with the LDA first. And so, same two options. Either we're stuck using only an ester that doesn't have alpha carbon hydrogens. Or we use LPA to irreversibly form the enolates and then introduce the second ester. And that you can actually mix and match these. If we wanted to add an ester to an aldehyde, then we wouldn't get something that stayed as a ketone here. We'd get kind of like halfway in between the two these mechanisms, right? So we'd still wind up with the blue one staying as an ester, but instead of this turning into a ketone, it would turn into an alcohol. Right, so we can mix and match these as well. That's a little bit more advanced, but it's the same something we just talked about. So anytime we have two things that are carbonyls, we can have them together in a variety of different ways if we control the order. So how would we use a Claisen condensation to make that one?
The platform would be the one like in between the two oxygens with the long.
There you go.
And then the section on the left is what we're doing left turns.
Good. So ethyl acetate. I don't think I did. Oh. It shouldn't have been in that in the first place.
Oh.
Because I was asked it that way. What molecule do we want to react with this heat rate? We use benzaldehyde. We use benzaldehyde, we actually get that case that I was just talking to you about where we kind of mix and match
Okay.
our ester with a class 2 carbonate. It would still work, but it's not gonna give us this. This would give us an alcohol in this position instead of a carbonate. We did ethyl benzoate. This comes in here, makes our tetrahedral intermediate that's going to look like so what if we don't have ethyl benzoate in our stopper?
Still nice.
We can go buy some.
Can we make it from the fence wall? Wait. What did I say the first time?
Benzaldehyde.
Yeah.
You could take benzaldehyde and you could oxidize it further to make benzoic acid. But benzoic acid we already have in the stopper. So if you take benzoic acid. So remember, anytime we want to turn an acid into one of our acid derivatives, we just need the right nucleophile.
Okay.
Right, we just replace the OH with a different nucleophile. So we might have to go back to our chapter and ask her just to remind ourselves the specifics, what the conditions need to be to do that. But an acid to an ester is pretty straightforward. An ester to an acid is pretty straightforward. So if we were going to be doing this, to Taylor's point, why don't we just buy it? If we were going to be doing this reaction every day, if this was the reaction we were studying with this molecule, we needed to make a whole bunch of it because we're going to keep using it over and over again for some reason. Then yeah, we would probably buy it.
Right.
Then we make sure it's easier. If we're doing this one time, we just need to do this once to test the reaction. We're probably not going to buy a whole new chemical for it. We'll make a chemical, especially one that's as easy, it's one step away from what we need.
Yeah.
Now we're getting, I know you all probably think we were already there. Now we're getting into the realm where everything is named after somebody.
Okay.
Because there's a specific type of Claisen condensation that gets its own name as well. Didn't we? Oh. Didn't we do this? We didn't do the rest of these?
We just did.
I jumped ahead. Okay, let's do B and C. Should we color them, making this more complicated than it needs to be. So our alpha carbon has the ester attached. And then it has the T-butyl group attached. You haven't seen convinced yet.
I just still don't like.
It's so the trickiest, the way that I approach these, that I try to walk it, I'll certainly say it out loud, is that identify your two active carbons, draw them attached to each other, our black line, and then say, okay, what is still attached on the blue side? Well, on the blue side, I lost this, so I still have a carbonyl, and then I have this. Carbonyl, this. And one of them, at least, you're usually going to be able to draw in the same orientation. You're almost never going to be able to draw both of them in the same orientation without drawing, like, a super long bond or weird angles. But if you can draw one of them in the same orientation, that simplifies things. And then I look at what my other active carbon is, the alpha carbon on this molecule, and you draw your alpha carbon. Then you say, okay, attached to my alpha carbon, I have my ester, and then I have this. For me, at least, I kind of have to break it up that way still to this day. And I've got a lot more practice than you do, and it still helps me. Like, this is the active part. This is the part that actually reacted. Then I go back and do my bookkeeping, basically. What else is still attached?
Maybe if I should have done to work at 12:15 and do 11:50.
Okay, I'm gonna stop it here for today. How are your, you can hang up while I'm asking you this. How are your finding your research articles going? Is that plus 2 DNMR enough for this weekend? Or do we want a quiz too? Yeah, we'll do practice. We'll start with practice with this in class on Tuesday. So no quiz this weekend. That makes my life easier too.
Okay.
So. You're not even going to UNR. I know you picked up more shifts, right?
Yeah.
Well, have a good weekend. Don't work too much.
Yeah.
Fun.